Hey everybody, and welcome to the Thermal and Electrical Conductivity Tech Talk. My name is Carlo, co-founder and VP of Applications at Fortify. I'm joined by my fellow co-founder and Director of Materials, Dr. Randy Erb. We're here to talk about Fortify's efforts in the creation of novel thermally and electrically conductive polymers in their applications. So in order to assess the opportunity fit of certain applications and markets, we use this framework as our North Star. This framework allows us to assess several attributes about how the benefits of our process and the benefits of additive manufacturing in general can provide value to a certain use case. To put simply, we look at three key attributes. One, does additive manufacturing provide a functional benefit to this application? Two, do functional additives such as fibers, particles, and other fillers provide unmet value? And three, do the economics of this application make sense from a volume and manufacturability standpoint? Through this exercise and through careful customer development, we've identified that Fortify can provide unique value for the creation of thermally and electrically conductive 3D printed parts. Now you might be asking yourself, why would anyone want to use a polymer-based material as opposed to a metal, which exhibits several orders of magnitude higher thermal conductivity than the competing polymer matrix composites? It turns out that there are many benefits to using polymers that are highlighted here below. First and foremost, polymers and plastics are easier to manufacture and shape. Secondly, for many applications, especially those involving liquids, metals exhibit corrosion and oxidation, while polymers are inherently corrosion resistant. Polymers are also electrically insulative, so they can perform in high power applications and exhibit reduced RF interference. Now, there have also been many studies performed on the efficacy of materials with lower conductivity values to ensure that there are still useful applicability. This figure highlights the materials with lower conductivity values between 1 and 10 watt per meter Kelvin still provide meaningful and adequate heat transfer, even when compared to aluminum. Some key applications areas for us that fully take advantage of the benefits of polymer-based thermally conductive materials are high power electronics, fluid heat exchangers, and lighting applications. Now, 3D printed ESD materials, on the other hand, provide many unique nuggets of value for those in industries such as electronic and PCB assembly. Oftentimes, ESD-related materials are injection molded or machined, leading to long lead times and limited geometric complexity. Additive ESD materials, on the other hand, require no CNC milling while still providing high dimensional accuracy. Combining ESD fillers in a high temperature photopolymer resin system enables the use of these materials in high temperature applications where this material would need to resist forces such as creep. Lastly, by printing these materials on demand, you can shave off up to 90% of the lead time for procurement when compared to traditional manufacturing. Some key application areas for us to fully take advantage of ESD materials are high power manufacturing aids such as jigs and fixtures, ESD safe required machine tools, and materials that operate in combustible environments. One of the key factors that are driving the market towards using additives in these applications is the fact that volumes are being driven down significantly due to several trends. Macroeconomic factors such as the electrification of vehicles require OEMs to consider more cost-effective manufacturing strategies such as 3D printing. Furthermore, design for additive manufacturing allows for performance benefits that are otherwise unattainable in traditional manufacturing. So, however, not all additive is created equal. All of the current 3D printing materials that are thermally conductive are thermoplastic based, which have limited scalability and complexity. DLP photopolymer 3D printing, however, can achieve best-in-class surface finish on manufacturing platforms that is proven to scale. By combining this with Fortify's processing capabilities such as CKM and Fluxprint, we are able to print complex thermally and electrically conductive components at scale. With that, I'm going to hand it off to my colleague, Dr. Randy Erb, to talk about some of the data.
Great, thanks, Carlo. So CKM, or continuous kinetic mixing, is a key hardware innovation here at Fortify. It allows for complete homogenization of filled photopolymers. It also allows for control of temperature of the resins to let us manipulate the viscosity and improve printability. CKM ensures that the first layer of our parts are the same as our last layer. In the next slide, we see a second key hardware innovation at Fortify, Fluxprint. This allows for the application of magnetic fields during the print, and it enables the texturing of the microstructure within particle-filled systems. Textured microstructure enables enhanced performance in mechanical, electromagnetic, and thermal applications. On the next slide, let's look at an example of Fluxprint. Not only can we align fibers within a layer, but inside a single layer, we can have different areas of different alignment. In this image, you see milled carbon fibers that have been doped and respond to the magnetic fields that we have applied. Now, imagine microstructures like this in materials that are electrically or thermally conductive. This is an exciting concept for tailoring complex conductivity pathways in 2D or 3D within printed parts. On the next slide, let's consider the role that alignment has on conductivity. We need to achieve exciting conductivities within polymers. And the key to this is percolation, in which the microstructure creates a connected pathway of conductivity throughout the entire part. We can see this in the following graphic. At low densities, conductivity follows a law of fractions modality. At higher densities, alignment can help drive percolation to connect particles and form a directed conductive pathway through the part. There is therefore a percolation threshold that becomes essential to hit to achieve meaningful conductivity. These thresholds are generally consistent with spikes in viscosity of a resin. However, field application allows us to purposefully move these thresholds to lower particle volume fractions while maintaining printable, albeit high viscosities. On the next slide, we highlight a unique opportunity for Fortify's approach to thermally conductive material. One of the unique opportunities we have identified is dielectric thermal conductors. Certain particles conduct through phonons and not electrons. We have found a unique place in this phase diagram on the right for thermal management materials. Our resins are both electrically insulative and thermally conductive. This combination creates exciting opportunities not accessible to metals in electrical and RF applications. On the next slide, we demonstrate that tailoring conductivity is possible with filler that is also electrically conductive. Here we see the first ESD photopolymer available enabled by our CKM technology. CKM allows for highly homogeneous and quite tunable ESD resins to be printed. In a first embodiment here, we present a resin that produces parts that are in the static dissipative classification. These parts are incredibly strong, high resolution, and speak to ESD applications. Back to you, Carlo.
Thanks, Randy. So we hope we demonstrated the value of 3D printed conductive parts through this tech talk. By filling and aligning our photopolymer composites, we imbue upon our components properties previously unseen in the 3D printing industry. So if you have any questions about thermally conductive or electrically conductive parts, please feel free to reach out to myself or Dr. Randy Erb with any questions you may have. Thank you so much for your time. Have a nice day.